interesting topics in material synthesis, patterning, and characterization, and it's all laying a foundation for what we really are here to talk about, which is energy storage devices. So I'm going to give you an introduction to the topic of energy storage devices this afternoon, and then we will move on and get into more details as the lecture sequence progresses. So whenever you're getting into a field, a relatively new field in particular, you have to learn the language of that field. And that's one of the most significant inertial barriers to doing new things. Now, for myself, I'm still learning. I did not study energy storage materials as a student. I was more looking at thermal problems. And so, these are things that I learned, picked up along the way, and I wish that there was a place that was really easy and where these definitions were consolidated. And so that's what I've tried to do for you, is to put these things together in a way that is concise but fairly complete. So lots of definitions. Why are the definitions there? Well, they're there because if you enter this field without knowing them, you'll be easily confused, and I don't want you to be easily confused. So I won't read these slides to you, but I will talk about some of these things. So the first thing is, when I test a battery or supercapacitor, at what rate should I be testing it? And so it seems like a really simple question, like you could just pick something and go. But it's really not fair to compare performance of a big battery to a small battery unless you are somehow normalizing for their size, okay? And so the C rate is something that you'll see used often. The C rate is the rate of current draw that you're taking out of a device in order to discharge it in exactly 1 hour. Discharge it fully in exactly 1 hour. Okay, so that way I can take a device that's really big and heavy, a large battery, and compare it to a small battery in a fair way. Okay, so that's what C rate is essentially means. E rate is similar, it's used much less. E rate is the same thing, except for you instead of having a constant current draw, you have a constant power draw out of the device. Now those two are really close to the same thing if the voltage is flat or close to flat. Okay, and we'll talk about the voltage profiles during discharge. So that's an important thing to recognize. And there's some example numbers in here that tell you that. The second category, these are mainly in descending order of complexity and sort of non-intuitive definitions. So the C rate and the E rate, you wouldn't really know unless you were in the field because there's no clues there. The other thing that's confusing is the definition of secondary and primary batteries. Right? It's not obvious what that means. A primary battery is what most people would call a non-rechargeable battery, a one-time use battery. And a secondary battery is a rechargeable battery. That's what most people call rechargeable. So there's a history behind why it's called those things, but if you don't know that going in, then you'll be easily confused. Some other things about voltages. So the terminal voltage is the voltage that the battery has when there's a load applied. And the load, of course, is resistive in nature, and so that voltage is going to be dependent on the resistance and the amount of current that's coming out of the device. It's a fairly complicated, it can be a complicated issue or characteristic. The open circuit voltage is easier. The open circuit voltage is what it sounds like when the battery is not connected to anything. What's the voltage across the leads? The internal resistance, we'll talk in the coming days a little bit more about that. the internal resistance is the resistance that's inside of the battery. It's part of the electrolyte, it's part of the electrodes, and as you might expect, the higher the internal resistance, the less efficient the battery will be, because resistance, when current flows through it, creates heat, right? And so that's non-useful energy. Some other definitions. I know there's a lot of words here. The nominal voltage is essentially what you would find listed on the battery itself. 2.8 volts, something like that. 3.6 volts. You'll see these have 9-volt batteries. That does not mean that the battery always produces exactly that voltage. What it means is that's the normal voltage for its operation. The cutoff voltage is the voltage at which we say the battery is empty or fully discharged, right? And so then, even though it's a finite voltage, you might think, well, maybe when it's fully discharged, there is no voltage, but that's not correct. In fact, there's quite a bit of voltage when it's fully discharged. It just can't produce any current, and then there's a big drop off. If you tried to draw more current out, what you would be doing is irreversibly reacting the inside of the battery with itself. There'd be side reactions that would happen, and you would have a dead battery after that, permanently dead. The capacity is usually listed in charge, so that's the number of charges stored. So amp hours. When you multiply current times time, you get units of charge, or coulomb. But that's not what is used for batteries, right? It's instead of using seconds, if you did amp seconds, you would get coulombs. But instead of that, you use hours for your time basis, okay? Now, the capacity actually depends on the C rate that we talked about earlier, right? If you draw charge out more quickly, if you discharge your device more quickly, you will actually have less capacity, in part because of the things we talked about. There'll be more thermal dissipation, okay? So you also, the amp hours are referenced to a particular C rate, but usually they're done in such a way that they're kind of in the moderate discharge rate, so not really fast, where things tend to be less consistent. The energy rating is done not in joules, which is the unit of energy. It's done in watt hours, which is power times time. Now, if you just like for the capacity in units of amp hours, the watt hours tell you how much power you can get out by taking the amp hours and multiplying by the nominal voltage of the device, because voltage times current is power, right? Amps times volts has unit of watts, okay? So that's also important to understand. Sometimes it gets a little bit confusing because you think of the capacity in amp hours, but what you really want to know is what you would need to know the voltage that the device is operating at in order to get the energy, right? And so usually all these things are listed. If there is one that's left out, oftentimes it's the energy term, but you can get that by taking the capacity in amp hours and multiplying by the nominal voltage, and that'll give you a good idea of the energy. Specific energy. This is one that's very important for research when we're comparing materials to each other. So the word specific in the thermodynamic context means per unit mass, usually. Sometimes it means per unit volume in context. So, but it's any normalized by size is really what it means. So when I say specific power, I mean the power per unit size. Usually that's in mass. Sometimes it can be given in units of volume. So the last term here is the float voltage. The float voltage is the voltage that you maintain after being charged to 100%. It's the voltage that you need to keep on the device in order to offset self-discharge. So no battery is perfect. If you charge it up, it's going to slowly leak current. There's going to be reverse flow from diffusion and things like this on the inside of the battery, even if there's no connection on the outside. And so to counteract that, you would put a small extra voltage on your device. That's called the float voltage. Okay, and that's defined here. All right, so if we look at this and looking at the capacity of batteries, I think it's important to understand what happens in the discharge process of a battery. So what I have shown here in this figure on the right side is the discharge characteristic. That's the voltage as a function of discharge amount. So the fraction of discharge. And you see that different chemistries produce different cell voltages. Well, that makes sense, right? We think of chemical reactions, and we understand that they're going to be associated with different thermodynamic potentials. And so in looking at this, different chemicals would likely have different voltages. Lithium ion is the highest. Lead acid is the next highest listed here, and then you get down into the nickels and zincs. The point of this curve is that, first of all, there are different levels of voltage, and that, if you think about it from an engineering standpoint, you have to match your voltages to whatever load you have, and certain loads will want to have particular voltages. So if the battery cell that you are using does not have the voltage you need, then you need to start thinking about stacking your battery so that you can produce enough of that voltage. Or same thing for supercapacitors, even more so for supercapacitors, as you'll see in a moment. But you also have to design, or someone has to design the load so that it can work with the battery as its voltage changes. And you see that these voltages are not constant. Some of them are flatter than others. The lithium ion is pretty flat at about 4 volts. The lead acid has a little bit more of a slope, but you have to, whatever you engineer the electrical system to do, it has to be able to accommodate a drifting voltage. You also use the voltage, you use this profile of voltage for a very useful feedback mechanism, which is it tells you the state of charge of your device, right? So when you think and wonder whether your phone battery is full or half full or whatever, it's really a reflection of this curve, okay? And your system kind of recalibrates itself. There are ways that it can recalibrate itself on the fly. Smart devices can do that. Supercapacitors are quite different, and I want you to appreciate this first and foremost. When a purely electric double-layer supercapacitor discharges, it does so it discharges at constant current. It does so in a linear way. So you saw those nice, almost flat voltage profiles from batteries. You could imagine, if you were an engineer, how it would be easier to design a load to work with a power source like a battery that has a flat voltage curve as it discharges. Well, capacitors are not like that. Double-layer capacitors in particular, as they discharge at constant current, the voltage drops linearly. And so that's not as easy a thing to handle, and you have to kind of do more with your electronics in order to accommodate these changes. Same thing with when it charges up. It charges in a linear fashion. The amount of energy stored in a device, in a supercapacitor device, is usually calculated by 1/2 CV squared. And the reason that you get a 1/2 CV squared is that your energy is really the integral of voltage as the voltage is changing. So it's an integral of V dV, which is going to give you a 1/2 V squared when you integrate that. So the factor of 3600 here is just from converting from seconds to hours. Now, that's the total energy in your device, 1/2 CV squared, but that's not the useful energy. Especially for capacitors, you have to look at what this threshold voltage is, because it drops so quickly, or this cutoff voltage. The useful energy is 1/2 C V squared minus the cutoff voltage squared. So the max is 1/2 C times the maximum voltage squared minus the cutoff voltage. Sometimes I would say it's easy to become enamored with capacitors just using 1/2 CV squared. But then when you're often disappointed when you have to subtract the cutoff voltage squared out of it, right? And so that's an important thing to do, and to recognize in a practical way that you do need to subtract out the part of the voltage curve that's not useful. So just looking at these, the capacitor and battery, we see here a comparison of the two. You have